After the race to the moon, the United States charts a new future with a new spacecraft. And a robotic mission to Jupiter struggles to get off the ground.
We started tearing this thing apart and really began to find the warts on it.
Meanwhile, another spacecraft attempts to complete the first reconnaissance of the outer planets.
The initial calculations showed that we were going to be in great danger of getting really fuzzy pictures if we didn't do something to the spacecraft.
ISS wide-angle electronics replacement heater is off. Iris replacement heater is off.
And at close encounter, we would all be holding our breaths. You can't believe how exciting that was.
The images that were returned this morning revealed a world unlike any of the others that we've seen.
Yet, even in the midst of triumph, the future of planetary exploration seems in doubt.
I'm kind of having a hard time reconciling all this to know what the next generation is going to be doing in space.
The footsteps of Voyager, JPL and the beginnings of the space age. Next.
I was strolling on the moon one day in the merry, merry month of December. Oh, May's the month. May, that's right.
In December of 1972, Apollo 17 astronauts Harrison Schmitt and Gene Cernan took the last steps on the moon.
Okay, Bob. Let me tell you, Bob, this flag is a beautiful picture. That's beautiful. This has got to be one of the most proud moments of my life, I guarantee you.
NASA had hoped for more missions, but the race against the Soviet Union to be the first to the moon had been won. America's priorities were turning elsewhere.
This is Gene, and I'm on the surface. And as I take man's last step from the surface, I'd like to just let what I believe history will record, that America's challenge of today has forged man's destiny of tomorrow. Godspeed the crew of Apollo 17.
Long before this moment, NASA was charting a new future with a very different kind of spacecraft. One with wings that could glide back to a runway. The shuttle, as it came to be known, could be reused over and over again to ferry astronauts and cargo into space. Early designs envisioned an enormous rocket flown by pilots that would launch the shuttle into orbit. This extraordinary concept was as unaffordable as it was unrealistic. The final design was severely scaled back. What did not change were expectations. Proponents promised that with this winged orbiter, access to space would become routine commutes. The shuttle was to be cheaper and safer. But to make the economic model work meant abandoning expendable rockets. The shuttle's manifest was to carry all cargo for NASA, commercial companies, and even defense and intelligence agencies. But the shuttle's reach went only as far as low Earth orbit, and that was not good news for exploring the solar system.
This was threatening the whole planetary program. But in this monopoly craze, NASA said, no, you can't just buy regular launch vehicles that were available. We're going to liquidate those. We're going to force them to close.
Bruce Murray was often out of step with NASA, but he viewed the policy of a shuttle monopoly as a threat to the entire space agency.
And so there were two issues. One was my programmatic view that this was a crazy thing to do and it it would, by the way, kill the planetary program, which it did for a decade. But more generally, it would destroy the agency. So the agency that had been able to do extraordinary things like Apollo was going to consciously transform itself to running a space transportation system because it had gained a monopoly. This was dreadfully wrong on both grounds.
Murray's criticisms were hard to see when the shuttle first flew. The shuttle not only looked like a space-age vehicle, it impressively performed like one. And Murray's opinions did nothing to discourage an enterprising group of JPLers from trying to hitch a ride on the shuttle. The team's leader was Charles Elachi, and he pitched a series of radar science experiments.
And basically the configuration of it at launch, it will be configured in this arrangement. Once we get in orbit, then the antenna panels will be opened, which will take about 1 minute operation to open the antennas.
NASA said yes to the proposal, and the second flight carried on board the Shuttle Imaging Radar A, the first in a series of radar payloads.
Okay, Sally, we've got the arm secured right now. We're just getting ready to activate the survey. We've got the power on and we're getting ready to turn it on.
Okay, sounds good.
The radar experiments demonstrated how the shuttle could be used to better understand our own planet. But for spacecraft destined beyond Earth orbit, the shuttle's limitations would be crippling. Jupiter. Only the Sun is larger than the fifth planet from our star. It is 2.5 times the mass of all the other planets in our solar system combined. The Pioneer and Voyager missions had provided the first flyby glimpses of this giant. The next step was to send an orbiter.
There was something called Jupiter Orbiter with Probe, JOP. And the science team consisted only of fields and particle people and atmospheric people. And they wanted to build a probe that would go into the atmosphere of Jupiter, and the simplest spacecraft to carry it there would just been a spinning spacecraft, and you could slap some fields and particles on the spinning spacecraft, and you had a winner.
Not everyone thought so. Other scientists were clamoring for different instruments and a camera. And that posed a dilemma. Taking images requires a steady platform, while measuring magnetic fields calls for a spinning spacecraft. To solve these conflicting requirements, NASA assigned the project to JPL in 1975. The result was Galileo, a novel engineering design featuring both spinning and stable platforms.
That quickly escalated into a really major, big design, big cost change, big mass change. And we started tearing this thing apart and really began to find the warts on it and attacked them one by one, but the spacecraft got bigger and more complex as a result of that.
Galileo also had the challenge of being the first planetary mission assigned for deployment by the shuttle. But to travel beyond Earth orbit would require strapping on a second booster rocket. There were 2 boosters from which to choose. One was the Centaur.
The problem with the Centaur is it's liquid fuel. If there's any kind of leak of the liquid fuel into the shuttle bay while they're trying to get this thing up in orbit, it could be potentially catastrophic, very volatile fuel.
The Centaur was seen as a dangerous risk, and NASA ruled out its use.
They were right, it was nuts to do that. It was not safe. So cancel that. And the only other thing we have is a solid fuel rocket called the IUS, which is actually an Air Force rocket developed. And you can use that, but that won't get you to Jupiter.
That was because the IUS booster was still on the drawing boards, and it was not powerful enough. To use this booster also required a gravity assist around Mars. The launch date slipped a year, resulting in the first in a long list of budget increases. Then it was realized that Galileo was heavier than the shuttle could safely lift. More powerful engines had to be built. NASA next directed JPL to explore dividing the mission in two, launching the spacecraft and the probe on separate shuttle missions. That plan was scrapped too. Galileo was again delayed.
They're just kind of back and forth, and every time the JPL engineers are kind of back to the drawing board, accommodating, different payload specifications, different trajectories they can accomplish. Every time they have to redesign the mission, and it's just a major headache here.
Galileo also became a political lightning rod. And now engineering decisions were being debated on the floor of the House.
Earlier this year, we passed a NASA authorization bill overwhelmingly in this House that said that we would go with the IUS. Now, you can vote any way you want to. I have no vested interest.
The problem here is that you have a vehicle that will get Galileo into geosynchronous orbit. It may be launched probably a year later, but as compared to the IUS and the kick stage, it will get there a year earlier.
The booster dispute finally came to an end when President Ronald Reagan signed a bill in 1982 that, by law, ordered NASA to use the liquid fuel booster. Galileo's launch date was delayed for yet another year, but at least there was now a path forward. Or so it seemed. Galileo survived. Bruce Murray did not. In trying to keep JPL's planetary missions alive, he had burnt one Washington bridge too many.
It's a real pleasure to be here. We at last have a director, and it turns out he's a pretty good director as far as I'm concerned. A man I'm proud to call my friend is Dr. Lou Allen.
Lou Allen was a four-star Air Force general with a PhD in nuclear physics. His resume included stints as deputy director of the CIA, director of the National Security Agency, director of the National Reconnaissance Office, commander of Air Force Systems Command, and Air Force Chief of Staff.
My space experience in the Air Force was almost entirely associated with the National Reconnaissance Office. These reconnaissance missions were, of course, different than planetary missions, but they weren't all that different. So coming to JPL was not a tremendous shock in the sense that it was a continuation, really, of the kind of work that I'd been doing for many years.
Whereas Murray had meant to shake things up, Allen's demeanor was calm and reassuring.
We who did not contribute to those accomplishments, but who have admired the work of this laboratory, envy you. And I consider it an honor to be able to join you now.
But there were concerns about how Allen's military background would be perceived, especially by Caltech, which manages JPL for NASA.
They were extremely self-conscious about the perception that they were bringing in this military general just when the lab was going to be ramping up defense work. And this perception that, well, now JPL is just becoming basically a de facto military lab.
Caltech President Marvin Goldberger instructed JPL to play down his military background. He was also worried that the news media might view a general's arrival as signaling a dramatic change and NASA's capitulation to the militarization of space. Goldberger declared there was to be no forsaking the civilian space emphasis for a military one, or an open R&D facility for a classified one.
So they worked hard to counter that perception. One way they did that was by referring to Lou Allen not as General Allen, but as Dr. Allen, because he did have a PhD in nuclear physics. He did have scientific credentials.
Before Allen's arrival, NASA's leadership had instructed JPL to take on work for the Pentagon, and the lab had complied. One involved the Strategic Defense Initiative. JPL's role was to find ways of tracking the path of incoming missiles that were to be destroyed by lasers. Another project was underway for the Army, an attempt to sort and analyze for commanders fast-moving and complicated events taking place on the battlefield.
That situation was so challenging to the Army that in some desperation they turned to JPL because they believed we were good enough and tough enough to make a breakthrough of sorts in this particular area.
But Dr. Allen's main interest was now space exploration. And early on, he announced that JPL would be actually reducing military projects to no more than 20% of its workload. And he articulated a policy restricting the type of defense activities the lab would take on and what it would avoid.
We should view the defense work in this way, that the JPL role should be early, that we make our contributions on the front edge of technology and phase out then of the programs just as quickly as we can.
This policy about military work coincided with a shift in Washington in favor of new planetary missions. Soon, Allen would have the best of worries: more work than the lab knew how to handle.
So our problems quickly shifted to the fact that we were outgrowing our facilities. So we tried different techniques for restricting the size of the workforce. None of them worked. The people at JPL who were out seeking the work were far too inventive to be influenced by a broad policy idea that one shouldn't grow. And so we continued to grow.
Earth science had been one growth area. Another was astronomy. The lab had played a vital role in the first infrared space telescope mission. And now JPL was busy building the workhorse camera for the much-anticipated Hubble Space Telescope. A radar mission to Venus was underway. So was an orbiter to circle Mars. There was even good news about Galileo. It was being packed up and shipped by truck convoy across the country to Florida. The spacecraft's next scheduled stop was the launch pad. Then it would finally be on its way to Jupiter. But as Galileo made its way to the Cape, another spacecraft already far beyond Jupiter was about to make history. After triumphs at Jupiter and Saturn, Voyager 2 was closing in on the first encounter ever with the ice giant planet Uranus. Voyager's journey to this point had taken over 8 years. And the wear and tear of 1 billion miles was beginning to show. The scan platform that moved Voyager's camera was prone to seizing up. Transmitting instructions to the spacecraft was an elaborate chore, as the primary receiver was no longer functioning and the backup was only partially working. Getting a signal back from Voyager was a challenge too. One-way transmission time now took 3 hours.
The extension of the mission to Uranus and Neptune, I think, highlights really one of the unsung heroes of JPL, and that is the Deep Space Network.
The Deep Space Network is a group of antennas arrayed in 3 strategic locations around the globe. This is the essential link for tracking and communicating with all of NASA's interplanetary spacecraft.
Those encounters at Uranus and Neptune would have been impossible without what the Deep Space Network, the DSN, did to get that data back. When you think about it, you've got the Voyager radio transmitter powered at about 23 watts, which is about the power of your refrigerator light bulb. And we're trying to pick up that signal here on Earth from well over 1 billion miles away. And picking out that very tiny little signal from that vast background of outer space is really a remarkable achievement when you think about it.
Plotting Voyager's encounter was another challenge. That was because compared to the rest of the planets, Uranus is flipped on its side, caused perhaps by a gigantic collision long ago.
Uranus was a real planning challenge, and the reason why is, one, we only get one shot, and two, Uranus is kind of turned up on its edge. And we're now, instead of seeing the moons in kind of a plane where you can fly through this plane and get one after the other, we're looking at a bullseye.
That meant that the flyby of Uranus and its moons and rings would occur nearly simultaneously. Coping with so much to see in such a short period of time would make this the most intense of all the Voyager encounters.
You're given this pulse of data no one's ever seen, and you get it all at once. You get high resolution, comes up very, very quickly because these moons are small and you're flying by it at large velocity. So in a blink of an eye, basically you go from a very low resolution image to in-your-face high resolution and then gone again.
You're going to go by every satellite in the same hour. It presented kind of a extreme version of the scientific competition between different targets. Everybody wanted to look in different directions.
As he had done at Jupiter and Saturn, project scientist Ed Stone listened to the arguments, sought consensus, and then made decisions.
I would take a poll, but it was not literally a vote in the sense, because I didn't feel that the science should be decided by vote. It really had to be decided on its value. And that had to be something that ultimately the group understood. In some cases, I had to make a decision where, in fact, it was really weighing two different objectives, and it was a judgment call.
The biggest worry was whether anything could be seen at all. Anyone who has ever used a camera knows that taking a picture in focus requires a steady hand and ample light. Voyager was moving at over 30,000 miles per hour, and sunlight at Uranus is 400 times fainter than at Earth.
One half of Uranus, in fact, was not even in the sunlight. The initial calculation showed that we were going to be in great danger of getting really fuzzy pictures of practically everything if we didn't do something. And so we actually did some re-engineering on the spacecraft with the help of the engineering teams.
Last year, my started at 0620 and ended at 0623.
We called it our anti-smear campaign. We basically improved our camera platform in flight by remotely changing how we operated it.
Scientists could also thank the navigators for their astounding precision. Voyager would arrive just a single minute off the predicted schedule, a schedule calculated 5 years before. Now came the mad rush to squeeze close to 100 measurements into just a few hours.
Off. Iris flash-off heater is off. There are no temperatures in the alarm. All items are as expected. Temperature is low, fixed at 32.
We were bringing our sleeping bags to our offices and sleeping overnight so that we could be there and not miss any of the great discoveries that were occurring on a regular basis. Even though we couldn't predict what they were, we knew there were going to be some great surprises.
The initial surprise, though, was the lack of a surprise.
We thought we'd see bands and other colorful things like we had seen at Jupiter and Saturn, and Uranus presented to us a blank face.
That first impression was deceiving. Uranus turned out to be the coldest planet in the solar system. Here, winds blow more than twice the speed of hurricanes on Earth. Another surprise was the planet's magnetic field. The poles here reside near the equator, twisting and turning like a corkscrew. And to everyone's delight, 2 new narrow rings and 10 tiny new moons were discovered. The biggest surprise, though, was the tiny moon Miranda.
Larry, I've heard you refer to this as probably the most exotic body in the solar system.
Well, I think exotic is an understatement. Miranda surpassed our wildest expectations. No one possibly imagined what we were going to find here.
Miranda just looked incredible. The amount of detailed structure, it looked like someone had just maybe like a clay or something sort of squeezed on it and given it all these different shapes and patterns.
Miranda was another one of these weird jigsaw puzzles of 2 or 3 different types of terrain that looked like you just painted them on the surface and then ripped apart the images and then put them together in some haphazard way.
It was clear that something had happened, some kind of activity had changed it from when it originally formed.
It was probably hit with something very large, which actually disrupted it, broke it apart. So you now have a big chunk of rock and a big chunk of ice, and these big chunks came together, which created these peculiar terrains.
This first ever visit to Uranus provided a bounty of discoveries. And NASA saw the encounter as an excellent backdrop to underscore to the press that 1986 was the agency's year of space science.
Thanks, Jim. It's been a real pleasure and a thrill for me, as I'm sure it's been for all of you. It's been a brilliant scientific achievement.
But the plan
It's been
backfired.
an enormous
These reporters were, almost to a person, unabashed supporters of exploring the planets. And the answer to one question had the effect of waving a red flag in front of a herd of disgruntled bulls.
This is pretty much the whole ball game, isn't it? None of us in this room were ever going to see anything else of any real consequence coming back from Uranus, are we?
As I just mentioned, it is very likely that there will be not be another mission to Uranus for a couple centuries. And so this is it.
To what extent is the fact that the United States does not have its own Halley mission a loss of face or a step backwards in terms of keeping the United States preeminent in space technology?
What follow-up plans you have for the follow-up stars?
I'm kind of having a hard time reconciling all this to know what the next generation is going to be doing in space.
What assurance can you really offer that the United States is going to continue to pursue planetary science and that when we see international missions, it won't be international without the United States?
Final question, Kelly Beatty, Sky and Telescope.
Dr. Edelson, at a meeting of planetary scientists in October, Dr. Allen stated that planetary science does not seem to be highly regarded within NASA. Would you like to comment on that, please?
Dr. Edelson?
Gosh, I didn't make that statement. Maybe I'd ask
I don't think
Dr.
so,
Allen
sir.
to comment on it.
I didn't write it down.
We do need to continue planetary exploration. There are things which are terribly important left to do. And it should compete in scientific importance with other important things such as the great observatories.
Ladies and gentlemen, our time is fleeting. Thank you very much, Dr. Edelson. Dr. Allen, we'd like to remind you that at 10 o'clock we'll
The
have
rush to get off the stage was telling. Expectations were far greater than funding. And in contrast to Voyager, the shuttle program was not living up to its billing. Access to space had not become routine, cheaper, or safer. Two days after the Voyager press conference, scientists at JPL paused to watch the launch of the next shuttle flight.
We were meeting in our daily science discussion meeting, and we had them through the weekends during that time period. And we had just finished discussing what we were going to talk about in the press conference that day. and it was time for the launch of the Challenger shuttle. And so we had a television set there in the room, and we broke our meeting up just in time to watch that. And
T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
And we were pleased that it got off the ground, and then suddenly we saw this bright flash and trails of material going in different directions. And it slowly dawned on us that the Challenger had actually blown apart.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
It was a tremendous shock.
We have no downlink.
We had 2 TV monitors up, one that was streaming the pictures of Uranus coming back, and the second with the repeats of the explosions of the Challenger. So hard to watch those. Success versus tremendous success with Voyager versus the heartbreak of what happened with Challenger.
The loss of Challenger and its crew of 7 was a major shock to the nation and an enormous setback for NASA. All shuttle flights were grounded. With no shuttle and no available expendable rockets, there was no doorway into space for the United States. Galileo was wrapped up and transported back to Pasadena. Other missions to Venus, Saturn, and Mars were placed on hold.
All of you recall, I'm sure, that 1986 was to be the year of space science. It began magnificently with Voyager's encounter with Uranus. But of course, the year of space science was brought to a tragic conclusion when the Challenger accident occurred so early in the year. We are overall looking at a substantial period of stand down in the achievement of space science information from the exploration of the solar system. Satellite programs will have to go into storage for a substantial period of time.
As NASA's shuttle program worked to recover from the loss of Challenger, Voyager 2 continued on its journey and final planetary encounter.
3, 2, 1. Just about 1 million miles left to travel for the robot Voyager spacecraft to the last planet in the solar system, its close approach to Neptune. Scientists are eagerly awaiting the close-up pictures of Neptune and its moon Triton, and project scientist Ed Stone says they'll be looking for more moons, too.
Neptune, 30 times as far from the sun as the Earth, very cold, very remote edge of the solar system.
Neptune is so far away that it cannot be seen with the naked eye. It was discovered only through mathematical calculations. This was the best telescope image of Neptune before Voyager 2.
It's very, very dark at Neptune. We knew that there were rings at Neptune. The rings themselves were half the brightness of soot, seen against a jet black background with sunlight which is 1,000 times dimmer than it is on Earth. So you've got everything going against you.
Once again, Voyager had to be retooled by remote control to have any hope of getting back usable images.
If the spacecraft is doing what it normally does, which is to slowly weave, bob around, it rotates around like this, you know, you're just going to smear everything. And so we had to go into the attitude control system and come up with very clever software changes to allow the spacecraft to stay very stable.
More advances in data compression were needed. A global array of antennas had to be lashed together, and Voyager itself was requiring attention.
The spacecraft has encountered its problems. It's deaf in one ear, essentially, one of the receivers. It's tone deaf in the other ear. It's got an arthritic scan platform. It's hung up on us several times. It's got memory lapses. It's got other, you know, the kinds of things you can associate with degradation, with age. But nevertheless, it's got a personality, and it's also got a brain.
And that brain had already noted a massive swirling storm, previously unknown moons and ring arcs. These were early signs that Neptune would not be a bland world.
It was a kind of an amazing encounter. I'm still not exactly sure why it happened, but it was a huge public affairs success.
With each encounter, Voyager became better known, and scientists and engineers were more media savvy. Some were even doubling up as news anchors.
We go to the opening,
yep.
We come to you,
right.
We say a few words, we say let's have examples of star occultation.
The Neptune encounter, I got to be the host of a PBS show called Neptune All Night. It was 4 hours of sitting there in front of a TV monitor for people who wanted to stay up all night for the encounter.
3, 2, 1, roll the opening.
Opening rolling.
Another anchor was a young engineer named Suzanne Dodd.
With us this morning, we have Dr. Jay Holberg.
I just got asked. I think JPL was looking for a young female engineer who knew something about the Voyager project and what Voyager was going to do.
Dodd joined the Voyager team right out of college. She had moved up the ranks and was now responsible for the commands that would have Voyager executing a daredevil flyby of Neptune.
I thought, okay, my career's kind of riding on this one because I built the closest approach sequence, and if it goes wrong, it's my, you know, it could be my fault.
A sense of drama was everywhere, and journalists and writers from all over the world were converging to be a part of what was being called the last picture show.
It was like a reunion. I mean, they came out here and they melded with the scientists. The scientists had a great time. They got a lot of good press coverage. It was a festival.
And at times, a feeding frenzy. No one knew that better than a Dutch-born, sleep-deprived JPLer named Yuri Vanderwood. It was his job to provide the always-on-deadline press with the latest images that were coming quite literally off the printing press in this era before the internet.
In those days, as soon as they saw you come in with the boxes with photographs, everybody had a deadline. And it was exactly 15 seconds from the moment they saw you.
Okay, just before you leave here, come by and I will get you a bunch of photographs to take home. All right? Thank you. Fantastic.
Then I had to turn around, go to the photo lab, and see what was coming in, as far as data is concerned, see how it was processed, then have 600 to 800 of those individual photographs printed of each, stacks of photographs that high. That had to happen through the night. But I had to stay there to get captions written and printed and glued on the back of each of the prints. 3 weeks I saw no bed. But boy, I wouldn't have missed a second of those days. There is no way you can describe, or I cannot, the feeling when you look at a planet for the first time in the history of our species. Nobody else has seen it.
It's kind of interesting. Beautiful pictures frequently are the ones that also have a lot of scientific content in them.
We've been in observatory phase for months, seeing Neptune as a slowly growing from a dot to something filling the television screen and more. Neptune itself is a beautiful, austere blue world. We are looking at a world of clouds and gas. The surface, if any, is far below. We have no idea what's deep down there.
And at close encounter, we would all be in von Karman holding our breaths. And you'd get these incredible pictures, which nobody'd ever seen before. And you'd sit there and you'd say, oh my God, you can't believe how exciting that was.
As Neptune's dark spot, the size of the Earth, came more into focus, other features became apparent too. Just below the dark spot was a group of streaking clouds circling Neptune so fast they were named Scooter. Here, winds blow over 1,200 miles per hour, the fastest in the solar system. Voyager was moving fast too, and flying low, skimming just above the cloud tops of Neptune. Then the gravitational force of the planet bent the spacecraft downwards towards the final flyby. Scientists who were accustomed to extraordinary sights were still amazed by what they saw at Neptune's moon, Triton.
Last night was certainly a night to be remembered. I think it's the most exciting night that I can remember from any of the encounters that we've had with Voyager, and there have been some exciting nights. Without a question, the images that were returned this morning revealed a world unlike any of the others that we've seen.
It seemed like a lot of these flybys often happened in the middle of the night or early morning hours, and that it seemed like that. And Triton was one of those.
Nothing like anything we've seen before here.
It is, so all the stuff is like Europa.
I think, well, it's like all of those things. Voyager put all the things we've seen before that was strange and put it in one place again.
I think for me, one of the highlights to see those early pictures come back and, you know, people pointing at the screen and saying, what do you think that means? What do you think is going on?
What is it? It's a crocodile of the solar system.
Europa all over again. It's Europa all over. Beautiful.
Oh, there are craters there.
What Voyager saw was a frigid world of rock and ice.
And it also had a very thin atmosphere. And the atmosphere had these cloud structures in it, these very, very thin, narrow clouds.
You guys see a limb haze?
That's a wind streak.
Oh, they're wind streaks, no question
How
about
can you have a wind streak with such a tenuous atmosphere?
You get the winds to
Follow
blow.
migrations, you had to blow very hard.
You get the winds to blow fast enough.
Yeah, but you calculate how fast it's got to blow in a several millibar atmosphere.
Obviously, it knows how fast to blow because it's certainly streaking that material out.
Triton had a very, very peculiar surface, very few craters, very odd, chaotic-looking terrain, very disturbed.
There are areas that look very resurfaced, right? I mean, craterless.
Here, perhaps, is the most diverse terrain in the entire solar system. Triton's surface has few craters, which suggests that unlike the moon itself, the surface is for some reason relatively young. A smudge on one of Voyager's images, so small as to almost go unnoticed, provided a clue as to why.
We saw these vents of things, and this thing is only like 20 degrees above absolute zero. I mean, it's one of the coldest things there is, and it's got things erupting on it.
And though these smudges were faint, the implications were spectacular. These were erupting geysers, shooting out material miles into space. In other places, there were lava-like flows of ice, all of it believed caused by volcanic processes underneath Triton's surface.
A world at the very, very edge of the solar system, frozen, we thought would be completely geologically dead, and it turns out to be geologically active. That was a great surprise.
I think we were all just overwhelmed with the experience it had been. I mean, this, for everybody, I think, on the Voyager team, been the journey of a lifetime. There's no doubt that the wealth of discovery from this mission had never been matched by any other mission. Voyager discovered the diversity of the solar system, which really told us that the solar system is alive. The objects in the solar system have evolved and are continuing to evolve. And I think for a science team, that was a unique experience, which will be the highlight for many of the careers of the Voyager scientists.
I think we should have a show of hands. Who's here from that 1972 imaging team?
I think it was very sad for some of the people on the project who had been there for all 4 encounters and really had their whole life revolve around these 4 encounters. They had their children in between encounters, and you could watch your family grow by the different years.
Okay, here's the Kennedy. We couldn't have done it without her.
So not only are you sort of done with the science aspect of the mission, but you're really losing your friends and your family as they go out and start working on other projects.
If I really think about what's happened in the last few days, it's intellectually perhaps one of the most stimulating times of my life. Emotionally, it's one of the saddest. I've been here for the last 10 years. I've worked on this mission and always anticipated one encounter after the next, realizing they'd be fantastic, realizing that there'd be things totally unexpected. And it's over. We've done it. We've finished the first reconnaissance of the entire solar system. We've rewritten the textbooks. What do you do next?
The adventures of the Voyagers were not over. In 1990, Voyager 1, over 3.5 billion miles away from its home, snapped these images. This first ever family portrait of the solar system was the idea of scientist Carl Sagan.
Hello from the children of the planet Earth.
Sagan also led the team that designed Voyager's golden record. It is a greeting card containing sights and sounds of our planet. Should one day, somewhere in interstellar space, a wayfarer were to stumble upon the spacecraft and wonder who had sent it on its adventure. A member of the record team, and later Sagan's wife, was Andrew Ann. Together they wrote this excerpted passage about our pale blue dot.
Consider again that dot. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. For the moment, the Earth is where we make our stand. It underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
At the end of the encounter at Neptune and Triton, celebration organized by Carl Sagan and the Planetary Society was held on JPL's Mall. The evening featured a surprise appearance by rock and roll great Chuck Berry. It was a fitting choice, as Berry's music was now sailing outward toward the stars aboard Voyager's golden record. That was only one of many reasons to celebrate. The shuttle was flying again. 3 months before the Neptune encounter, the shuttle Atlantis had deployed JPL's Magellan. This spacecraft used radar to map the surface of Venus in 3D. It was a natural follow-on to the pioneering experiments JPL had flown on the shuttle's early flights. 5 months after Magellan's deployment, Galileo was also deployed and sent on its way to Jupiter. Magellan and Galileo were 2 of only 3 planetary spacecraft ever carried aloft by the shuttle. Lou Allen retired in 1991. He used this skit to help say his goodbye, riding off into the sunset with his wife. Allen died in 2010. Ed Stone became the new sheriff in town. Even while serving as JPL's director for a decade, he continued on as Voyager's chief scientist. In 2013, Stone, still the only chief scientist Voyager has ever had, announced that Voyager 1 had reached interstellar space, the region between the stars. This historic event happened during the watch of Voyager's 10th project manager, Suzanne Dodd. All this was still ahead, but on this evening of the Neptune celebration, before Chuck Berry struck the first note on his guitar, Carl Sagan addressed the assembled crowd with words that are as fitting today as they were in 1989.
Every human culture has rites of passage. They mark the transition from one stage of life to another. We are gathered here to celebrate Voyager's rite of passage. A machine designed, built, and operated right here at JPL has broken free of the sun's gravity, explored most of the worlds of the solar system, and is now on its way to the great dark ocean of interstellar space. The men and women responsible are gathered here. They are heroes of human accomplishment. Their deeds will be remembered in the history books. Our remote descendants may live on some of the worlds first revealed to us by Voyager. If so, those descendants will look back upon us as we look on Christopher Columbus. Voyager reminds us of the rarity and preciousness of what our planet holds, of our responsibility to preserve life on Earth. If we are capable of such grand, long-term, benign, visionary, high-technology endeavors as Voyager, can we not use our technological gifts and long-term vision to put this planet right? To take care of one another, to cherish the Earth, and bravely to venture forth in the footsteps of Voyager to the planets and the stars.